before I talk about inverse matrices, which is what the main topic of today is, I actually want to talk about something called an identity matrix. So some of the stuff that we're going to talk about today, I'm going to take a little trip down memory lane to what you know about real numbers and try to make the connections between these real number properties and how they apply in matrices, because it's kind of the same idea. So I'm going to talk about this thing called an identity matrix. A quick note, an identity matrix has to be n by n, so that means it's square. It has the same number of rows that it does columns. And I'm going to denote the identity matrix with the capital letter I, so that means that that's the identity matrix, and the sub n on that I just means for whatever number of rows and columns it has. So if I do I sub 2, that's a 2 by 2 identity matrix. If I do I sub 5, that'd be a 5 by 5 identity matrix. Now, the property of the identity matrix is, remember these capital letters all mean matrices. If I take some matrix A and multiply it by the identity matrix, then I get matrix A. So identity property is really you're going to add or subtract, multiply, and get the same thing that you already were. In this case, it's multiplication. And let's just take that trip down memory lane. I'm going to use some big words here, but just think about them and see if you can give me the answer. What is the multiplicative identity value for real numbers?
1.
1. Why did you say 1, Liam?
Because anything times 1 is itself.
Yeah, because anything times 1 is itself. That's what the idea of identity actually means. What is the additive identity in real numbers? 0, because if you want to add something to a number and still get the same thing, it would be 0. Okay, so the context of identity matrix is still the same thing. If you multiply some matrix by the identity matrix, you get the same matrix. Okay, so here are some examples of what the identity matrices look like, and these are going to be the two that you're probably going to encounter most often, 2 by 2 and 3 by 3. So they remind us when we had that discussion about row echelon and reduced row echelon form that kind of fit that definition of reduced row echelon form. It only has 1s and 0s. And then really important is, in order for it to be the identity matrix, you're going to need this diagonal of 1s going down from left to right. Okay? So you could imagine, and you could extend this to 4 by 4 and 5 by 5s. Okay, you got to have that diagonal of 1s. Everything else is going to be a 0. Now, just so that we can kind of confirm the identity matrix does the thing we think it will do. Sorry, I lost my cursor. Let's practice multiplying by the identity matrix. Am I close to that little X over there? Can you see me? Get rid of that. There. Oh, I changed the color. I went too far. Thanks. Okay, so we already know what should happen here, right? It's 2 by 2 times the identity. So we should get the same thing. Let's just kind of see how the identity matrix actually works. This is 2 by 2 times another 2 by 2. So of course we're going to end up with a 2 by 2. I'm going to take my first row times my first column. So 3 times 1 is 3. And then add negative 1 times 0 is 0, so I just get 3. And then multiply it by the next column. 3 times 0 is 0. Negative 1 times 1 is negative 1. Can you see how those identity columns work? It puts zeros for all the numbers you don't want in that entry, and then it has the 1 for the one that you do. So we want this next entry to be negative 5 so that it's the same matrix. So negative 5 gets multiplied by 1, but then 2 gets multiplied by 0. So we end up with negative 5. And then negative 5 times 0 and 2 times 1, and we're left with 2. Okay. Now, I did a 2 by 2 square matrix, but you could imagine, like, I could have a 1 by 2, I could have a 3 by 2, as long as the columns in that first one matched the 2 by 2, the rows in the second one, I could still multiply and I would end up with the same matrix. Okay, now let's get into the business of this inverse matrix. Up at the top in blue, I don't think you necessarily have to write this down, but I'm going to ask you this question. So we had talked about multiplicative identity was 1. What's the multiplicative inverse of the number 2? What do we think? I heard Elena, negative 1/2. Do you agree with her? Dylan, you say? You thought it was 1/2. I agree with 1/2. Okay. So the multiplicative inverse of 2 is 1/2. I'm going to ask this question. Why is the inverse of 2 1/2? Okay, it's being flipped. It's the reciprocal. Yes. And when you multiply them together, they equal 1, which we just identified 1 as the identity value, right? So 2 inverses multiplied together to give you identity, okay? And that's why you can solve equations using inverse operations. The inverse undoes the other thing, right? Okay, so that's going to be a big concept here for us when we get to solving systems. Let's talk about the inverse matrix real fast. We have to let A be n by n. So notice A has to be square. So we can only do inverses of square matrices now. And this has to be true if 2 matrices are inverses of each other. So remember, all my capital letters just mean I'm talking about matrices. And we've seen this notation with the negative 1 before. It just means inverse, right? We've seen it for functions. So it's saying matrix A times the inverse of matrix A is equal to the identity matrix. And the inverse of matrix A times matrix A also equals the identity matrix. Like 2 times 1/2 is equal to 1, and 1/2 times 2 is also equal to 1. They both equal the multiplicative identity, which is why they're so useful for solving. And remember, that sub n on my I just means for whatever dimensions my square matrix is. Okay, so let's show that matrix B is the inverse of matrix A. Matrix A is 2, -1, and -3, 1. And matrix B is -1, -1, and -3, -2. Knowing what we know so far about inverse matrices, how could we show that they are inverses? Yeah, we don't know a lot, right? We just know that if we multiply them together, they should equal the identity matrix, the one with the 1s and the 0s in it. Okay. So let's do it. Let's multiply them. I'm going to do A times B. Now this is 2 by 2 times a 2 by 2, so my answer is going to be another 2 by 2. I'm going to take that first row in A and multiply it by my first column in B. So 2 times -1 is -2, plus -1 times -3, that's +3. -2 plus 3 is 1. And then do my first row times that second column. 2 times -1 is -2, And then it's going to be plus a positive 2 for negative 1 times negative 2. So that's 0. Is it coming out to what we think it should? Yeah, let's just verify. Second row. Negative 3 times negative 1 is positive 3, and then 1 times negative 3 is negative 3, so we're going to come up with a 0. And then we'll get a positive 3 and a negative 2, so that's a 1. Now, what else would be true about these two matrices? What's that, Jackie? A is the inverse of B, so we could also check it the other direction, right? So B times A would also equal the identity matrix. It wouldn't matter what order you multiply them, they both equal the identity matrix. And I'm not going to work that out, but that is true. Do you remember on Friday at the end of the pink notes that we did in class, there was the question, is matrix multiplication commutative? And what did we decide on Friday? No. Okay, it doesn't always work. In fact, you could end up with like two entirely different orders if you switch the order that you multiply. But if they are inverses of each other, multiplication is commutative. They both come out to be the identity matrix. So there are some special cases where matrix multiplication may be commutative. Now we need to get into the other part of like how do we find inverses. So go ahead and make sure you get this in your notes. It's going to be really important. I'm going to tell you how to calculate a 2 by 2 inverse by hand. And so this could be included on the non-calculator portion of your exam for matrices. This is only for 2 by 2s. And we're going to let A, matrix A, be the matrix with entries A, B, C, D. Now, if those are the entries in A, this is how you would find the inverse. So I'll give you some time to copy it down, and then we'll talk about all the things that are happening right there. So this would be your inverse. And remember that negative 1 is just a notation for inverse. So there's sort of two things at play when you calculate a 2 by 2 inverse. One of them is that you're going to have a scalar out front. So that 1 over AD minus BC, that's the scalar that you're going to have to distribute into your inverse. Where are we getting AD minus BC? Like when you look back at the original matrix A, how do you describe AD and BC? Where do they come from? The diagonals on the matrix, right? Okay. So you're really doing the product of the diagonals. A times D is that diagonal going down from left to right. B times C is the diagonal going down from right to left. So you're doing the difference of the product of the diagonals. Okay, so you can draw that X and get those two diagonal values. Now you have to go in the right order. It has to be AD minus BC. Okay, otherwise you get the wrong sign. And then the other part of the inverse matrix is this like 2 by 2 matrix. Now remember, it's not the same matrix. It's not A, B, C, D. Can you describe some things that are happening to the entries? How are they being rearranged or changed? Put that in your own words. Okay, Brian gave us 2. Swap A and D. Right, just switch their positions. So on the blue diagonal, swap the positions of those two numbers. On the red diagonal, do the numbers change position? No, the numbers stay where they are, but they change signs. Okay, so change signs. Okay, If they're positive, make them negative. If they're negative, make them positive. Awesome. Before we leave this, I'm going to give you one question. So you can only do inverses of square matrices, but not all square matrices have inverses. So I'm going to ask you this question. When would an inverse not exist? When wouldn't you be able to find an inverse matrix? Tell your group, when do you think an inverse doesn't exist? Have that little chat. Hey group, got a good idea for us? When does an inverse not exist? Clear, concise, Dylan? When AD minus BC equals 0? Yeah. Because then you'll have 1 divided by 0, which is undefined, and that's not going to give you a matrix. Okay. So you could also say like when AD and BC are the same, because then you subtract them and you get 0. Okay. But yeah, either one of those would be fine. Okay, excellent. Okay, so let's practice finding an inverse for the matrix A, 5, 4, and 2, 1. Okay, I'm going to show all my work because these are my notes, so I want to be able to look at this later and know where my numbers came from. So the inverse of A is 1 over, and I'm going to show my work for the diagonals. So first diagonal is 5 times 1, which is 5. It's always subtract between the two. And then the second diagonal is 4 times 2, which is 8. When I do those on like my homework, I probably do that in my head, 5 minus 8. If I'm going to show my work right now. And then I'm just going to get a new 2 by 2 matrix. So remember the 2 steps Brian gave us. On the blue diagonal, switch the positions. So it's going to be 1, 5. On the red diagonal, switch their signs. So negative 4, negative 2. What is the actual value of your scalar then? Negative 1/3. Okay. So we're going to have negative 1/3 times this matrix, 1, negative 4, negative 2, 5. And then, like, to give me my final answer for an inverse matrix, you should distribute the scalar. So don't leave the scalar out front. Give it to all the entries. So my inverse matrix would be negative 1/3, positive 4/3, positive 2/3, and negative 5/3. There are a lot of times when your inverse is going to have fractions in it. I mean, just consider the fact that you're doing 1 over AD minus BC. There are going to be some nice times. I love having AD minus BC equal 1. I love it when it equals negative 1. But anytime it equals some other value, I'm likely to get a fraction of some kind in my inverse. Okay. Any questions or concerns so far? Okay, if your matrix is 3 by 3, you're going to use your calculator. So let's everybody get out our calculators and practice this. Of course, you have to begin by typing the matrix into your calculator. So get to your matrix menu. Okay, so I'm doing second, x to negative 1. Remember, you got to go over to edit. Okay, and I'm going to edit matrix A. I'm going to make it 3 by 3. So I got my matrix A typed in. Okay, and then once you get your matrix typed in for your 3x3, remember you're going to do second mode to quit. You're going to get out and go to your computation menu or screen, and then you're going to go pull matrix A or wherever you put this matrix. Go pull that matrix again. So go back to matrix menu and grab A. Now, that button that you've been using to get to the matrix menu, it looks like x to the negative 1. So that's just your inverse button. So now instead of hitting second on that button, just hit that button. So it's right above your x squared. It's going to look like A inverse. And then I hit enter. I think on yours, Jayla, you're going to have to just raise it to a negative 1. Because like you type yours in, right, Jayla? Now, did you also get some decimals? Ugh. Okay. So, some of you already know about how to turn decimals into fractions on the calculator. Some of you may not have known that this was an option, but it is. If you get decimals in your inverse and you don't want them, then just hit math. And the first thing in the math menu is frac. So just hit enter. And like if you have like the answer there saying like, do you want me to put your previous answer in as a fraction? Yes, please. And then I get these nice over 11s. Okay, so we'll do it for all of my entries. Okay. Anybody having any trouble in their calculators, let me know. I will try to address this best I can. So you have, no, I would say you'd rather have it. So I would, probably a number, do you have like a decimal? Yeah. Yeah. I'll try it again. Okay, any questions, concerns? Can you take a calculator class? Oh, you just like learn them as you go. And also, you guys have to know, like, go to YouTube, right? There's all the tutorials on YouTube. When I want to know how to do something, I just go to Google and YouTube. There's so much that I probably don't know, Eli. All the cool things in my calculator could do that I don't know about. Okay, now you don't have to write this part down, okay? But would you just look over this solving equation and do you agree with everything? Like, I guess most people when they do 2x equals 10, they would say divide by 2. And then I would say, okay, but what are you really doing when you divide by 2? And then you would answer back with multiply by 1/2. Only because I want to make the point. Someone else gave me 1/2 was the multiplicative inverse of 2. I think Dylan gave that to me before. And why was that the case? Because 1/2 times 2 was 1 and gave me the identity. Now, we usually don't write the identity out, right? There really is a 1 right there representing the identity for the product of the inverses. But then we get our solution. Okay. So I'm going to show the work to solving a matrix equation using this method. And we're going to shorten it so we don't have to do all the in-between steps. So remember how last week we did row echelon form? We wrote things in augmented matrix and then we did row echelon form. This week we're going to do things differently. Today we're going to start with a matrix equation. So it's an equation filled with different matrices. And we're going to, in our matrix equation for our system, we're going to have an A matrix, we're going to have an X matrix, and those two things multiply to give us B. Now, you'll see me put a system into this equation on the next slide. Okay, but we're going to have 3 matrices multiplying together. I'm using capital letters, so that's all matrices. Okay, now, if it was a number like 2x equals 10, I will multiply by the multiplicative inverse 1 over 2. Okay, if it's a matrix, I'm going to multiply both sides by the inverse matrix. And the inverse matrix of A is just, we write A inverse. So I'm going to put A inverse on this side, and then I could do B times A inverse, but I know ahead of time that you'll always have to reorder it. It will always be A inverse times B. That's the only way you'll be able to multiply them by dimensions or orders. What happens on this side with A inverse times A? It cancels. It actually equals. Remember, you're working with matrices. The identity matrix. Okay, so those equal the identity matrix, which essentially is the same idea as 1, right? But it's got a bunch of entries in it. And then we have this A to negative 1 times B. And again, I'm trying to cut out all the work. Maybe we just kind of like jumped ahead there, Elena, when you said it cancels out, right? It cancels out, but it really equals identity. But then identity times x is just okay. So x equals the inverse of A times B. Okay, so on the next slide, step 1 is going to be to write the matrix equation. Step 2 is kind of like in the middle. I'm going to need to figure out what the inverse of A is. And then I don't need you to write out these 2 steps because they always work out the same way. The inverse times the matrix always equals the identity. It's always going to be the inverse times B. So you can just jump right down here, and this is going to be step 3. So you're going to be doing some matrix multiplication down there. Okay, let's put this to work. We're going to solve a system. It's going to be 2 by 2, so it's going to be no calculator. Negative 3x plus 4y equals 5, and 2x minus y equals 10. Okay, currently it's just a regular old system of equations, but I need it to be in matrix form. So one option last week was to write the augmented matrix. That's a single matrix that we changed into row echelon form. Today, we're going to write a matrix equation. So remember, my matrix equation had 3 matrices. Matrix A, matrix X, and matrix B. So here's A times X equals B. A is your coefficient matrix. X is your variable matrix. And B is on the other side of the equal sign. It's those constants. Because we're going to be solving with inverses, we need to have a square matrix. So we're just going to use our coefficient matrix. That's going to be square for us. So drop in your coefficients. Negative 3, 4, 2, negative 1. What should I put in the variable matrix? X and Y, the variables. Very good. And then my constants are going to be that 5 and negative 10. Now, if you pause just momentarily and you think about matrix multiplication that we did on Friday, this really does write out your system. If I took row 1, negative 3 and 4, and I multiply it by this column, it equals the first entry over here. So it's saying negative 3x plus 4y equals 5. That's the first equation. And if I do row 2 times the column, it should equal the second row. So that would be 2x minus y equals negative 10. So it really is writing the system. Okay, what are we going to need in order to be able to solve for x? We're going to need the inverse. So let's do the work for the inverse matrix. That's the inverse of A. So this is going to be 3 minus 8, which is negative 5. In that 2 by 2 matrix, switch the values on the first diagonal, change the signs on the other. And then because my scalar is negative and all my entries are negative, when I distribute, they're all going to turn into positives. So A inverse is 1/5, 4/5, 2/5, 3/5. No worries. But now I want to use that inverse to solve the equation. So remember, if matrix X, A times matrix X equals matrix B, it's true that matrix X is equal to A inverse times B. So my variable matrix, XY, is equal to 1/5, 4/5, 2/5, 3/5 times 5 and -10 matrix. Now, you can end up with fractions, right? We had that conversation. It's very common to get fractions in a determinant, or sorry, not a determinant, in an inverse. But, you know, when you do that 1 over AD minus BC, if you don't reduce, then you'll have common denominators. So that will kind of make your life a little bit easier. I didn't have any that did reduce, okay, but I could leave it with a 5. So that would be common denominators. And then I'm just going to do like regular multiplication. Take row 1 times column 1. So when I do that, 1/5 times 5 is 1. And then 4/5, I'm going to write this out. 4/5 times -10. Yeah, I would just think -10 over 5 is -2, isn't it? So then that's -8. So my x value is -7. Not too bad. Doable. And then 2/5 times 5 is 2. 3/5 times -10. Again, -10 over 5 is -2 times 3 is -6. So then I will have a -4. So -7, -4 is my solution. Now remember, at some point, you'll get the option when you see a system. Do you want to solve it algebraically? Do you want to solve it with matrices? Do you want to do row echelon form? Do you want to do inverse matrix equation? Right? You have options. So some of us may see, oh, that's a lot better than row echelon form. Okay, any questions or concerns? Okay, so I could ask you to do a 2x2 on the no calculator part. If you had a 3-variable system, you would have to use your calculator. I think I used the same coefficient matrix as our previous inverse. So if I go to my calculator, I think if I pull up matrix A from before, if you did the last problem with this, I'm just going to pull up matrix A and hit enter. That's the same coefficient matrix, right? Okay, so if we wanted to solve this, we've already got the coefficient matrix in the calculator as matrix A. We also got to put in matrix B. That's going to be our constant matrix. We don't need to put in the variable matrix. We just need the A matrix and the B matrix. Okay, so then I would go to my matrix menu. You could go with me. And leave A alone. You already have that one in there. Matrix B. Oops, I forgot to edit. Edit matrix B. And this time you want like a column matrix, so it's going to be 3 rows, 1 column. So put in -4, -23, and 38. So you enter that matrix. And then on this screen right here, remember that statement. If A times X equals B, then X equals A inverse times B. So I just have to tell the calculator to do A inverse times B. So I'll go to the matrix menu. I would choose A, do the inverse, and times by b. I don't even really need to see what the inverse matrix is, right? I'm just writing that little statement. A inverse times b. And then I know x is -3, y is 4, and z is 3. So not too bad. Okay? Questions, concerns? Okay. You gotta practice that calculator stuff so that you feel confident that you could do it on a quiz or in a test. Okay, you do have a homework assignment this evening, and that's on your gold sheet. Just a reminder about Chapter 7 test retakes that's due next Tuesday, so you should have checked out your test, and you should be working on the retake correction, or the test corrections and the retake assignment. And then I'm going to hand back your quiz here from Friday in just a moment. So if you're getting your quiz back, you need to fix it for tomorrow. And you're going to turn it in tomorrow no matter what you've done, and then you'll get a grade for it. I don't want you to use the yellow quiz correction sheet because it's only one problem. So some people have space on the back, or some people might want to just like get out a piece of loose leaf and do it on a piece of loose leaf. That's fine. Some things that showed up that were mistakes for us, and these are like in list of seriousness down to like lower. So like some people did row multiplication, which was never a row operation. So you shouldn't be doing that, like row 1 times row 2. Some people kept doing row operations, but they never got a leading 1 or 0. So that just kind of left me wondering, like, what was your whole goal the whole time when you were doing all those different things to your rows? Okay. Sometimes when you make a fraction through a row operation, you might reconsider your previous step. Like, oh, I don't like having that fraction right there. Was there another way for me to have gotten a 0 or gotten a 1? Okay. It's not that it always has to be. A lot of people on the first row just multiplied by 1/3 as their first step, and then they had a fraction for the rest of the work. So every time they did something with that row, they introduced more fractions, and that got messy for them. And then, of course, sign errors and computation errors were the other thing. Okay? So I'll hand that back to you, and I want that back to